Alright, well, we got about 2 minutes left, but I'll go ahead and get started anyway, just to have something to talk about. It has been a long time, but before break we had a test. If you guys remember, we had a test on counting and probability. Before that, we did some logic, and we did other things like that. And so a lot of those things are using to build up to what we're going to get to today. And today we're going to actually start talking about proofs. And so we're going to start giving proofs of different theorems. Now, in order to be able to do some fun proofs, or some worthwhile ones anyway, what we're going to do is we're going to have a couple definitions first. And so we're going to look at things like divides. So we're going to say that n divides m if m is equal to some integer times n. So for example, 2 divides 4 because 4 is 2 times 2. 2 is an integer, so we get 2 divides 4. However, 4 does not divide 2 because if we try to write 2 as an integer times 4, it wouldn't work out. Now, the reason why we're using this terminology instead of saying, like, what is 4 divided by 2 is because for the real numbers, division isn't always defined. We can always ask, does 2 divide 4 or does 4 divide 2? And that becomes a statement then that we say 4 divides 2. So it's true or false, and we can determine a truth value. But if we say find 4 divided by 2, well, if we try something like 4 divided by 0, then we don't have an answer. But we can say 4 divides 0 or 0 divides 4, and we can determine the truth or truth values of those different statements. So as opposed to using division, we're going to use this definition to work with a divides thing. Now what's going to happen is if we do try to divide, we will end up with certain times where we don't get an exact division. So if we take 5 and try to divide by 2, we're going to end up with a remainder. And so what we want to think about is, in general, if I have any integer and I have any natural number, can I divide a by b and get out something? So what we're going to do is go look at that on the board. And what I have here is something like, let's start off with 5, and let's try to divide it by 2. So now if I want to try to find 5 divided by 2, well, what we could do is long division and say 2 goes into 5, and then, well, how do I do this? Well, I multiply by the biggest number I can to get out a number still less than this, and then it ends up being something here, and then we can continue on. And the point here is that as an algorithm, trying to define long division is actually rather complicated. So what we're going to do instead is try to define an algorithm or a process to find the division, which is easier. And so if I want to take 5 divided by 2, what I want to know is how many 2's can I pull out of 5? And the way I'm going to do that is first, I'm going to take 5 and I'm going to subtract 2, and I get 3. Well, 3 is positive, so that means I get to subtract at least 1 2. I'm still positive, and in fact, 3 is still bigger than 2. So now I can take 3 minus 2, and I get out 1. So what that means is that from 5, I was able to subtract 2 twice, and I'm going to have a remainder of 1. So I can write 5 is equal to, because I subtracted 2 twice, that's going to be 2 times the number I'm dividing by 2 plus 1. And now what you'll notice here is that 1 is less than or equal to 2. And so in general, we want to think about how would we take any number a and divide by a number b. And what we're going to do there is, let's say I have a and I want to divide by b. Well, I can follow the same process and I can get a and I can subtract b. Now, what might happen is if b is bigger than a, this is negative. So eventually we're going to, or here we're going to get a negative number. If that's the case, I would just say that a divided by b is a is equal to 0 times b plus a. And notice that we have a as an integer times b plus an integer where 0 is less than or equal to a is less than b, assuming here that we have a and b are positive numbers. Now, on the other hand, if b is smaller than a, then I get a minus b is going to be greater than 0. And so I can say, well, I get a minus b is some new number. Let's call it a sub 1. Now, with a sub 1, I can say, well, let's find a sub 1 minus b. If this is less than 0, then what we do is we stop and we would say that, well, that means that b is bigger than a1, so a would be equal to 1 times b plus a1, and now we've written a as an integer times b plus an integer, where this integer is between 0 and b, which is what we're looking for. We're trying to rewrite numbers in that form. However, if this is still greater than 0, then what we end up with is we can call this a2, and then we can subtract b. And we can subtract b, and we can subtract b however many times we need to, and eventually we're going to get some a sub n such that a sub n minus b is less than 0, whereas a sub n minus 1 minus b is going to be equal to this, which is greater than 0. Greater than or equal to 0. Now the point here is that if I have a positive number and I keep subtracting some other number, well, if I subtract 2 from some huge number and I keep subtracting 2, no matter how big this number is or how small this number is, as long as they're integers, I keep subtracting this over and over again, eventually I'm going to end up being smaller than 0. So if we go back one step, we would be positive, and so this is exactly the point we're interested in. And so what we'll notice here is that we were able to subtract b. So 1, 2, n minus 1, n times. And so we're able to subtract b n times and still have a positive number. But if we try to subtract it n plus 1 times, then we got a negative number. So what we would say here is that, okay, if this is the terminating point, I would say a is equal to n times b plus my a sub n here. And we know that 0 is less than or equal to a sub n is less than b. And so this is the division algorithm. If we want to divide a by b, we would subtract however many times we can. We count those up. The number of times I subtracted is going to be n. And so a is n times b plus, and then my remainder is the a sub n. And I know that's going to be between 0 and b. So I can set this up so I divide, and notice that b will divide a if and only if this remainder is 0. Because if this remainder is 0, then a is an integer times b. If it's not 0, then we can't have that. You guys have any questions on that so far? Go ahead. What's your question? So that's a great question. So we have to be very careful about how many times we subtract it. And so if I subtract once, I get my a sub 1 is still going to be positive. If I subtract 2, I get my a sub 2, which is still positive. And so this would be once, twice. And so here I would have subtracted it n times to get my a sub n, which is still positive. So if I count these correctly, I did subtract n times here, whereas this would be the n plus 1. Oops, thank you. All right. So if we go back to the chalkboard, sorry. I took A and I subtracted B once, and I ended up with A sub 1, which I said was still a positive number. And then I subtracted it twice to get A sub 2. So if I'm just trying to keep track, then I would have A sub 2, and the third time I end up with, sorry, this should be equal to A sub 1, which is greater than 0, is greater than 0. And so this would be the nth B that I've subtracted. So therefore, I've actually subtracted n b's to get from an minus 1 to an. So that means we've counted, if we count these up properly, we end up with, I think we get exactly n. Now, if you had defined this differently so that you would start with a1 and subtract b, and then this is a2, you could have something in the case where this would be an n minus 1. But the way I've defined this algorithm, I'd have exactly n times that I've subtracted b. And that's why, okay, if I've subtracted b n times, then I can say a is n times b plus a sub n. That's a great question of, is this n or is this n minus 1? It's something that you really have to be careful about and follow exactly through each of these steps of how many times did I subtract it to get to each point. And so if you were going to do something like run this type of thing on a computer, you'd probably set up a counter to say how many times did I actually subtract it, so that I can tell you how many times you subtracted it. And the point here is that this division process can actually take a long time. However, intuitively just realizing, okay, I'm taking a number and I just keep subtracting until I get smaller than 0. And then if I go back to the point before where I was bigger than 0, that would be the point, or I'd have to count up the number of times I've subtracted it. So then I can say A is the number of times I subtracted B plus whatever remainder I had left over. Is that okay? All right, very good. Dominique, the question was, how do we know if it's n or n minus 1 times the b? And so that's what I was trying to explain. I'll try to be better about restating the question each time it comes up. All right, trying to get back to the correct screen here. So what we're going to have now is, if I divide, that's how I'm going to divide. And so we're going to work with some simple things like, what if 2 divides n? And so if 2 divides n, then that means by definition that n is 2 times some integer. And if n is 2 times some integer, then we're going to say that n is an even number. So an integer is even if 2 divides n, that is n is 2 times some integer. And an integer is odd if it is not even. That is, 2 does not divide n. All right. So what we've done here is just, we've talked, hopefully you've seen even and odd numbers before in different texts or different situations, but we're trying to give a formal definition. So now with that formal definition, what I want to point out is that we can do something like prove a theorem. So most of that stuff there was definitions. We want to set things up. Now we're ready to actually prove something. And so what I want to prove is that if an integer is odd, then n equals 2a plus 1 for some integer a. And the second theorem here is the reverse, is that if n equals 2a plus 1, then n is odd. All right. I saw somebody said they couldn't see what I was writing, so I will try to write more legibly and bigger. But what I want to point out here is that we have an if-then statement. So if P, then Q. So if I have if P, then Q as a statement, if we remember back to our logic, remember that in general, an if-then is true if P is true and Q is true, or P is false and Q is true, or P is false and Q is false. So the only way this is false is if P is true and Q is false. So if we want to show that this is true for all things, or all the time, the point here is to show that this is always true is that, well, we don't actually have to worry about when P is false, because if P is false, this thing becomes true. So what we have to do is we say that, okay, well, assume that P is true. We have to show that Q can't be false. So we want this to always be true. So that means that we can't have the situation where P is true and Q is false. So in order to give a direct proof of an if-then statement, what we're going to do is we can assume P, and then eventually we're going to have to show Q. So the setup for our proofs using what we call a direct proof is we assume the if part, we show the then part. If we can do that, if just based on this assumption we get out that the then part is true, then this statement always has to be true. Therefore, that's a theorem. And so that's how we give a valid proof of when this is true. So now I'm referring back to the logic sections. Hopefully we can kind of recall some of that. But that is the basic setup for our proofs. Any questions there? All right. If not, then what I'm going to say is that, well, in this case, what we wanted to do is say that if n is odd, then n can be written as 2 times a plus 1 for some integer a. So what I get to assume is that n is odd, and I have to show that n can be written in the form 2a plus 1. All right, so now, before getting too far in here, I just want to say that what we've done here is we've just set up the proof. This is, we get to assume this, we have to show this. And so now there's stuff to do in the middle. And what I want to do is kind of outline a general practice for how we're going to do that. But proofs, just like if you guys remember from calculus doing applied problems, are, well, each one has a similar outline, but a different process in the middle part somewhere. So our outline here is going to be to assume the if part, show the then part, and then what we're going to do is some more things to try to help ourselves out, and then there's going to be some middle part where we have to guess what's going on. These aren't going to be easy, so as you guys are doing your homework, don't feel like you have to get it right on the first time. You can get it wrong a few times. That happens, so don't be afraid of that. Just say, I'm going to keep trying until I get it. But to help us out, we're going to use this process saying, okay, well, let's start off. If n is odd, then n is not even. And I'm just going to rewrite the assume part in any way that I know. So it is not even. So therefore, 2 does not divide n. All right. Now I can look at the bottom and say n is equal to 2a plus 1. Can I rewrite that in any simpler form? Well, I don't really see anything. That's a nice form. It's just an equation that I have to show, so I just have to show n can be written in that form. All right, what I have to do now, and this was the hard part I was talking about, is figure out how to get from here to here. So, how do we do that? Well, we have to be creative. And the reason why I went through those definitions and I went through the division algorithm to begin with is because now we can use these to actually do a proof here. And so what I'm going to say is that I want n to look like this. So I'm going to just say n is equal to, and I'm going to try to write n equal to stuff. Well, what I do know is that by the division algorithm, I can write n is equal to 2 times some integer a plus, let's say b for now, for integers a and b. So I'm just going to say a and b are integers. Furthermore, 0 is less than or equal to b is less than 2. All right, let's make sure we grasp what's happening here. Is I'm using the division algorithm, so I'm taking a number n. I know I can divide by 2 and get something of the form 2 times an integer plus an integer, where this one is between 0 and 2 because I'm dividing by 2. However, what are the only numbers that are between 0 and 2, not including 2, is this means that b is either 0 or 1, because those are my only options. Now, can b be 0? You guys can help me out here. What happens if b is 0 in this case? Then n is equal to 2a plus 0. And n is even. Very good. Thank you. So someone chimed in on Discord. Thank you for that. If b is 0, then n is even because it's divisible by 2. So we can say b is not 0. Or otherwise, n is even. I know I'm getting tight in here, so I'm going to erase some of this stuff. N is equal to 2a plus b. b is not 0 since n is not even. But I've just said that b was either 0 or 1. Those are my only options. So if it's not 0, it has to be 1. But if I just read what I wrote, b has to be 1. Therefore, n is 2 times a plus 1. So we get that every odd number can be written in the form 2 times an integer plus 1. Whereas every even number can be written as 2 times an integer. Now, the importance here is that even and odd are kind of vague ideas, just 2 does or does not divide it. But having nice formulas that we can substitute in is going to help us do theorems later on where we can say, okay, if n is even, it looks like this, so we get this. All right. So the question here is, how do I rewrite this? Does it have to be the way I write it at the board? And the answer is always, no, it does not have to be the way I write it for you guys. As long as it follows a logical progression, you can write these proofs up in many, many different ways. I'm trying to outline one here that kind of follows the thought process that we went through. And because I said, okay, I know it can't be 0, then n is not even, that's what I wrote down. If you saw it as, oh, well, doesn't matter if you write good or not. In the beginning, Not really. I'm going to go that far and say, right now, what I want to see is your thought process, and I want you to be able to write out. I'm going to go back up to the board. So what I want to see is your thought process, and so I want to be able to say, okay, this idea led to this idea, led to this idea, led to this idea. Now, if you want this to be nice and pretty, we'll talk about that a little later in the class on how to do that. But for right now, I really just want to see that logical progression. I don't need full sentences at this point. I don't need full paragraphs at this point. I just want to see your thought process and see that you can lead from one argument to a next argument through small steps to eventually getting out what you're looking for. Now, eventually, yes, you would like to have this. Oh, can you guys hear me? All right. Just to point out, I can actually talk in Discord, but you'll probably hear it twice. So I haven't been talking in Discord. So I have been talking only through the live chat. So you'll have to see the live chat to hear my responses to you. All right. And all right, so yeah, to get to the point, and actually what happened was I wasn't sure which way to do that, but when we were doing a testing stream, someone suggested I only do it through YouTube instead of talking through both, so that's what I'm trying to do. I think it's a little nicer for you guys. All right, now back to what we were talking about, which I completely forget what we were talking about. Oh, the writing stuff. We will talk more about how to write properly throughout this class to get you used to it. But as far as my expectations for this class is I don't expect pretty proofs and things that are elegantly written during this class. However, I want to get you to the point so that by the end of the class you can start to write elegant proofs so that in the next math class you are ready for that. The first proof class, yeah, it's not expected that you have a great writing, so I really just want to see your thought process. Does that make sense to everybody? All right, good. So now I have the converse here is that if n is 2a plus 1, then n is odd. I'm not going to go through that one, but I do want to say that that's also true. Because if it is 2a plus 1, then if I try to divide by 2, I'm going to get a remainder which is non-zero. Therefore, because my remainder is non-zero, n is not divisible by 2, so therefore n must not be even. Therefore, n is odd would be an outline of that. But the point here is that by showing both directions, we actually get if and only if. So if whenever I say something is odd, you can say it looks like 2a plus 1. Or if I say something looks like 2a plus 1, then we know it's odd. And so having these different ways to write things is going to be extremely helpful in proofs because a lot of times what you end up doing is just trying to rewrite things in different ways so that it makes sense within the context of the problem to show you how to get from the if part to the then part. All right. So now here's what I'm going to do is this is a proposition. So what is a proposition? A proposition is just a theorem. There is no real distinction. However, we do have words like proposition and theorem and lemma and corollary, which all just mean theorem in a slightly different context. So if you're looking through the book and you see these words, you don't necessarily need to treat them differently. But a proposition is generally a theorem which isn't as exciting as a real theorem. And a lemma is a theorem which isn't as exciting, but is used to prove something that is exciting. And a corollary is something that isn't as exciting because it follows directly from another theorem. So basically, if I use theorem, it means exciting theorem. If I use proposition, it means still exciting but less exciting theorem. And if I use lemma, it means theorem used for another theorem. And corollary means a theorem following directly from another theorem. I just wanted to point that out because those words will be used as we're lecturing and in the book, and I don't want you to get confused by them. You can treat them all as the same thing, but when I'm using different words, I'm trying to give context for how this is going to be used. All right, so now we've gone through one together. What I want you guys to do is actually set this up and say, if x is odd, then x squared is odd. How would I prove that? So to help you out, it would say I would assume something, and then I have to show something. So write down what you think you should assume. Write down what you think you should show. And then write definitions that are equivalent to each of those things until you can connect the dots. I'm going to give you a minute, and then I am going to do that together with you. All right, so I don't expect you to be completely done, but hopefully you guys can see. In this case, what should I assume? Very good. So we're going to assume the if part. Very good. So we assume x is odd. What then do we have to show? X squared is odd. So I assume the if part, I show the then part. All right, sorry, so I'm trying to read this text here. All right, that has nothing to do with this class. The derivative of the improper integral. I think I'm going to leave that question there, and I might answer that some other time, but since we're talking about x is odd and x squared is odd, I'm going to stick to this proof. Now, what we have is we get to assume this, and we have to show this. So if we get to assume this, and we have to show this, the next thing we're going to do is just say, well, what does it mean for x to be odd? Well, that means x is 2 times, and instead of a, I'm going to use k1 plus 1 for some integer k1. And the reason why I'm using k1 here is I'm going to have to use another number down here, because if I want to show x squared is odd, I have to show x squared is 2, let's say k2 plus 1 for some k2 and z. I know that's getting jumbled in here. I'm trying to put it up here. But what I'm trying to say is that something is odd means that, or is equivalent to, because we just proved this, x is equal to 2 times an integer plus 1. And so if I get to assume x is odd, I get to assume this. And if I have to show x squared is odd, I have to show x squared is 2 times an integer plus 1. So using this, I have to prove this. All right, and so now we're back to the middle part here where we have the middle part here where we have the hard part of determining how to get from point A to point B. And so we have to be a little creative here. And so the thing we're really going to do here is a common thing, and we're going to use a substitution. So we're going to start with x squared, and we're going to write a bunch of stuff out until we get out 2k2 plus 1. So just so I have enough room, what I get is x squared is equal to, well, if I substitute, we know that x is equal to 2k1 plus 1. So x squared is 2k1 plus 1 squared. So now, through some arithmetic, we can square this out, and we get 4k1 squared plus 4k1 plus 1. We spent time distributing these out when we're talking about the Pascal's triangle. So I'll let you guys kind of do that on your own, but if I do square that, I get this. Now remember, the goal is to get this to look like 2 times k2 plus 1. So I'm even going to write that in. This is where I'm headed. So I have to decide, can I make this look like this? Well, what happens here is, if I look at this portion, I can factor out a 2. So I get 2 times 2k1 squared plus 2k1. And then I'm going to leave the plus 1 off to the side. And you'll notice that, well, this is just 2 times an integer squared plus 2 times an integer. So this is just an integer. So if I let 2k1 squared plus 2k1 equal k2, then we get that this is just 2k2 plus 1. So to recap, what we've done is we've said, okay, I know x is odd, so x squared is equal to 2 times k1 plus 1 squared. So I substitute in the x. I'll do some arithmetic. Notice here I factored out the 2. And I said, oh, this is just an integer, so let's call it k2. So I got x squared is indeed in the form 2k2 plus 1. So that means that x squared is odd. Hence, if we can assume x is odd, then x squared is odd. And so we have proven our proposition. Do you guys have questions on that? It is not related to hyperbolic sines. So the point was that we wanted to prove that x squared, sorry, I actually thought that was white. That is not white. We wanted to show that x squared looked like 2 times some integer plus 1. This was the goal. So if we kind of go back and remember, we had to assume this was the then. This is what we have to show. So we wanted to show that x squared looks like 2k2 plus 1. So in order to do that, what we did was we just said, well, we have 2 times some integer plus 1. So we wanted it to look like this, but we noticed that this is just an integer. So 2k1 squared plus 2k1. So instead of writing this all out all over again, we're kind of simplifying the writing and just saying, okay, we're going to denote this by k2. So that then what I get is 2, this whole thing is k2 plus 1, so that we get the x squared in the form that we want, so that we know that this is an odd number. So, easy answer here is that we introduced the k2. That's supposed to be a k1. We introduced the k2 so we don't have to write this. I'm sorry, go ahead. Oh, okay. Yes, this should just have been a k1. I just got excited about my k2. It's like, hey, look, it's going to be there. And then I put it here instead. Sorry about that. All right. So, what I want to work on next is here's another proposition for you. And what we have is if A divides B and B divides C, then A divides C. So notice here we have a new theorem that we need to prove. And what we need to do is say, okay, if the A divides B and B divides C, so we get to assume both of those, we have to show A divides C. So again, I'm going to give you guys a minute here. Try to set this one. Say, assume this, then this. And then if I get to assume this, what is that equivalent to? What's the then equivalent to? And try to work your way back and forth until you get to the middle part. I tried to block the people who were trolling in the chat, so hopefully that helps out, by the way. I don't know if I was able to permanently block them or just put them on timeout, but I tried to get rid of them. All right. Georgie, I have questions, but I can't seem to get them answered here. I do check this chat, and I do try to answer your questions the best I can. However, especially when I'm at the board, it's hard to read the chat. So if you go to Discord, you can actually chat with me through voice chat, and I'll hear you even when I'm at the board, so then I can give you a direct response. And that's why I wanted to use both YouTube and Discord so that you could talk to me while I'm doing things like writing at the board. All right. Now, if we go to the proof of the... They are recorded, so you're welcome. The lectures are recorded, so you're welcome to... Yeah. You're welcome to review them anytime. If you can't make lectures in the future, feel free to come back to them. They will be there for you. It's one of the reasons why I decided to go this route, so that I could do it. All right. So going back to the proof, what we want is A divides B and B divides C. All right. I knew that was happening, and I went over to try to check it. I didn't see the name, but I think I got one of them. If you guys see the names, just shout out the names. I'll come back and mute them. All right. All right, we'll do that. I did think about that before, about only posting it in Blackboard. I just was trying to make it easy on my students, and I guess other people wanted to come in and troll. I've never actually had that happen to me before, to be honest. I was never important enough. I don't know if I'm proud or just really upset right now. But in the meantime, I am going to get back to this problem, and I want to show. Okay. So I want to assume that A divides B and B divides C, and I need to show that A divides C. So what does it mean for A to divide B? Well, this means that B is equal to... Oh, thank you. There we go. So I get to assume A divides B and B divides C. I need to show that B is equal to A times K1. I get to assume this, and I get to assume that C is equal to B times K2. So K1 or K2 are some integers. And what I have to show then is that C is equal to A times, let's say, K3 for K3 an integer. All right, so now that's the setup. This is my assume, this is my then. This is equivalent to this, and this is equivalent to this. So now again, what I need to do is fill in the middle here. So if I want to fill in the middle, what I'm going to do is I'm going to use some type of substitution again. I'm going to start with C, and somehow I want to get out A K3. So what is C equal to? Well, C is B K2. And we know that from this part of the assumption, we get to use that. So maybe you guys can help me out here. What would be my next step? Can you guys still hear me? Or are you just not responding to my question? So we're going to rewrite this as the formula that we had above. And so what we get is B is going to be A K1. And so we get C is B K2 and A K1 times K2. And so if we rewrite that, we get A times K1 K2. Now, if we notice, K1 is an integer, K2 is an integer. So what does that mean? Well, it means that we can let K3 equal K1 times K2. K3 will then be an integer, so we get C is equal to A times K3. And again, we're using that trick here. We know this is an integer, so we're simplifying it to write it as a number. So we get A times K3. So C is A times K3. Therefore, A divides C. So starting off with A divides B and B divides C, we do indeed get A divides C. So again, we're using start with C and substitute things in until we get what we're looking for so that we can get out the theorem that we're trying to prove. All right. And so my next one here is, suppose that I have two integers, A and B have the same parity. So now what does same parity mean? It means that they're both even or both odd. The only reason why I use that term is because it's in the book and I wanted to give you a heads up on it. So then what I want to show is that the sum of A and B is even. Now this one's a little bit different because we are focused on an or here instead of an and. In the last one, we got to assume A divides B and B divides C, so we get both of these things at the same time. However, when we're working with this parity thing, we're going to end up with an or statement. So that is, we're going to get to assume that A and B are even, or A and B are odd. So if we get A and B are even, or A and B are odd, then what that means is that we're actually going to have to break this into cases, because I don't get both of them. I get one or the other, so at least one is true. So the process here, and we want to show that A plus B is even, the process here is that we'll assume this one and show that in this case this has to be even. Then we'll assume this case and show that in this case this has to be even. Therefore, if this part is true, then this part is true. If this part is true, this part is true. And since this or this is true, at least one of those is true. Therefore, we've shown that if this is true, then this is true. And so with an AND, you get to use both, but with an OR, you have to break this into cases and do one step at a time. So case one, I'm going to say A and B are even. I then have to show that A plus B is even. All right, so now if A is even, what does that mean? Very good. So that means A is divisible by 2 and B is divisible by 2. So what I get is A is equal to 2k1 for some integer k1. I also get that B is equal to 2k1, or k2 rather, because I need another integer, for some integer k2. And what I want to show is that A plus B is equal to 2k3 for some integer k3. Does that make sense so far? All right, so I get A plus B is 2k1 plus 2k2. And so I'm starting with A plus B. I'm just going to substitute this in. But notice that I can factor out a 2, and I get 2 times k1 plus k2. So what I would do here is notice that k1 plus k2 is an integer, so we're just going to define k3 equals k1 plus k2. So we get A plus B is indeed equal to 2k3 for some integer k3, so therefore A plus B is indeed even. And so that's case 1 of the proof. What would case 2 of the proof look like? Well, instead of even, we would have odd. So instead of this, we'd have plus 1. Here we'd have a plus 1 because we know that an odd number looks like 2 times an integer plus 1. So if I do this substitution in here, I get 2k1 plus 1 plus 2k2 plus 1, which, I'm going to need some room here, is just equal to 2 times k1 plus 2 times k2 plus 2. So again, I can factor out a 2, and I get k1 plus k2 plus 1, because 2 divided by 2 is 1. But again, k1 plus k2 plus 1 is indeed an integer. Therefore, A plus B is 2 times k3, or my integer. So therefore, A plus B is again even. Therefore, what we see is that if A and B are both even, or if A and B are both odd, then we must have that the sum, A plus B, is indeed going to be even. Do you guys have any questions on that one? All right, then. With that in mind, I just want to point out that thank you for sticking with me. I'm sorry we had some people trolling us in there. But we learned how to do a direct proof today, how to actually show that an if-then statement is true and will always be true. And notice that the things we proved today always have to be true. There's no way that they could ever be false. So we now have things that no matter what in the world happens will be true, which in some respect is a really nice thing to hear. But I hope you guys learned something. Please start looking at the homework for this chapter, and I will formally post the homework on Thursday for you. I think there were some questions. There is no homework due tonight, but it'll be due next Tuesday. So if you start looking at those problems, you can get a head start and start thinking about, okay, well, how do we prove things? On Thursday, I'm going to pick up with the proof things, and I'm going to talk about proofs using different techniques than just direct proof. Any questions before I let you guys go? All right, well then, thank you very much for joining me. Class will be the same time on Thursday, so I'm going to stick to the same schedule you have for actual classes. I know I'm letting you go earlier than class officially gets out, but I feel like proofs, there's a lot to take in, so I feel like it's okay to let you go a little bit early to digest what is going on. I think Sammy asked me if there was any homework. There's no homework due tonight, but you can start looking at the homework from the direct proof chapter in your textbook for next week. Any other questions? All right. Thank you very much then.